Hi everyone. In this video, we're going to continue our discussion of the calculus of exponential functions. In the previous video, we proved this derivative formula for the natural exponential function. But we haven't yet developed a formula for a more general type of exponential function such as a to the x. Now, if the derivative of e to the x is e to the x, you might reasonably guess that the derivative of a to the x is a to the x. And you'd be almost right, but you also need to multiply by the natural log of a. Notice this formula would imply that the derivative of e to the x is actually e to the x ln e, which initially looks different from the formula we came up with before, so let's make sure this doesn't contradict our findings from the previous video. Keep in mind that ln is short for log base e, and we know that asking for the value of log base e of e is the same as asking e to what power is e. But e to the power of 1 is e, so this logarithm has a value of 1. And so this expression simplifies to e to the x times 1, or in other words, just e to the x. So we can rest assured this is consistent with what we already know about the derivative of e to the x, and that is a good sign. But at the end of the day, this new formula still needs proof before we can use it. So let's see if we can calculate this derivative. As a first step, what I'm going to do is apply the natural logarithm. But I can't just apply a logarithm and expect not to change the function entirely. So I'm going to cancel out the act of taking a logarithm by applying the corresponding exponential, the inverse function. What we're looking at here is still just a to the x. I've just written it in a different form. But the advantage is that I've manipulated this into a natural exponential, and we already know how to take the derivatives of those types of functions. So knowing the derivative of e to the x is e to the x, we can say the derivative of e to the something is e to the something, times the derivative of that something according to the chain rule. Next, we're going to simplify a bit using laws of logarithms. For starters, we can apply a cancellation law, and we can also bring this exponent down. Now we still have to calculate the remaining derivative, and the key to doing that is to notice that ln of a is just a constant. So how do you take the derivative of x times a constant? Well, think about it. The derivative of 2x is 2. The derivative of 3x is 3. In general, the derivative of x times a constant is just the constant, which in this case is ln of a. So this here is the derivative of a to the x, and it looks like it's supposed to, so this completes the proof. As soon as we discover any new derivative formula, we'll get a couple other important formulas for free. For example, how would I take the derivative of a to the something if that something is not just an x? Let's call it a u instead. Well, you would take the derivative as if it were just an x to get a to the u ln a, but don't forget to apply the chain rule, meaning multiply by the derivative of the something. In this case, the something is a u, so I'd be multiplying by the derivative of u. And now that we know how to take the derivative of a to the u, we can also find the antiderivative of a to the u. The antiderivative is a to the u over ln of a. This last formula isn't something that's immediately obvious based on what we've done so far, so let's prove this. Keep in mind that asking for an antiderivative of a to the u is the same as asking for a function whose derivative is a to the u. So this is what I'd like to know. Is a to the u over ln of a function whose derivative is a to the u? If it is, then by definition, it's an antiderivative. So let's take the derivative of this and find out whether the answer to this question is yes or no. For starters, you can recognize that the denominator is just a constant, so we don't need to do anything with it when taking the derivative. As for the numerator, we know the derivative of a to the u is a to the u ln of a. And notice there's no need for the chain rule here because I'm taking the derivative with respect to u, not with respect to x. Now, after simplifying, we can see that this derivative really is a to the u, so the answer to my question is yes. A to the u over ln of a is a function whose derivative is a to the u, so it must be the antiderivative. And that completes the proof of this integral formula. Also, don't forget to write all these ones down on your formula sheet. Let's try putting these formulas into practice. So see if you can calculate this derivative on your own, and when you're ready, let's look at the answer. Here we want to differentiate 3 to the power of something. We know the derivative of 3 to the x would be 3 to the x ln 3, so the derivative of 3 to the something would be 3 to the something ln 3. Just don't forget to multiply by the derivative of the something according to the chain rule, which in this case, my something is root x. And after taking the derivative of root x, you can present your final answer. Now let's try this example. Pause and come up with an answer of your own, and when you're ready, let's continue. It's important to notice that this is a variable raised to a constant, not a constant raised to a variable. So this isn't an exponential function, it's a power function. So all you need to do is use the power rule on this one, and you're done. Next up, let's do an antiderivative. Pause and try it for yourself, and when you're ready, let's look at the answer. There's actually more than one way to do this, but one way is to try and think of this as 2 to the u, since that's the formula we know from earlier in the video. Just be cautious. If you want to call this 2 to the u, you need to actually do a u substitution. And that means you need to keep track of the impact this has on du as well. So checking those details leads us to this result, at which point we know the integral of 2 to the u, so just use the formula from earlier in the video, and don't forget your plus c. Also, make sure to express your final answer in terms of x. I'll show you another way this could be done, since when it comes to integrals, it can be really helpful to have multiple perspectives. So going back to the beginning of the problem, if you notice the exponent here contains multiplication, we can use an exponent law to express this as 2 to the 2 all to the x. But that's just another name for 4 to the power of x. And if you see the integral in this way, there's no need to do a u substitution. Well, I suppose you could say u equals x, but then du equals dx anyway, so there's really no point. So go ahead and directly apply the formula from earlier in the video to get 4 to the x over ln 4 and present your final answer. That's all for the calculus of general exponential functions, so I'll wrap things up here and see you next time.